В основном все пришли обратно, но не докладчик, кажется. Причем, так. Да, извините, пожалуйста, дорогие коллеги, это очень неприятная и полная неожиданность. Да, Катя, вы снова подключились?
Да.
Да, ну все, простите, ради бога, тогда можно продолжать.
Ага, давайте тогда с 2020 года еще начну сейчас. Так, сейчас я расшарю.
Да, извините, ради бога.
Ничего страшного. Видно, да? So in 2020 shared task, we decided to increase typological diversity of languages because languages differ in many ways. Some exhibit rich grammatical case systems, so some mark possessiveness, and others have complex verbal morphology, such as Ottoman languages, or even decline nouns for tense, such as Tupi-Guarani languages. So let's discuss some dimensions such as fusion, inflection, synthesis, and position of case suffixes. So according to Walls, languages differ from oscillating to concatenative. Concatenative morphology is the most common system. And there are some non-linearities such as ablaut or tonal morphology. Tonal concatenative morphology can be found in Mesoamerican languages. In terms of inflectional synthesis of the verb, so analytic expressions are common in Eurasia, and synthetic expressions are used to a high degree in the Americas. So finally, in terms of position of case suffixes, so languages vary from prefixing, suffixing, infixing, and circumfixing. So suffixation is common in Eurasian and Australian languages, and for instance, prefixation in Mesoamerican languages or African languages spoken below the Sahara region. So, and of course, as like in NLP community, people often note that there are certain language-specific biases. For instance, Emily Bender notes that architectures, training, and tuning algorithms still present language-specific biases. So in this shared task, we tried to investigate systems' ability to generalize across topologically distinct languages. So we had 19 languages from 13 language families. So, and we ran this shared task in 3 phases. So development was 2 months, and we provided training and development data for 45 languages from 5 families. Generalization phase was just 1 week, and we provided training and development data for 45 languages from 10 families. And finally, evaluation phase was also 1 week when we released all test data for 90 languages. So in this year, we had a huge annotation effort. So we basically took some grammar books and then manually converted their language-specific features into Unimorph format. We then canonicalized the data. Still, some of the languages were very under-resourced, such as Zarma, Tajik, Lingala, Ludian, Maori, and so on. So, and for the systems, so we provided several baselines. So one of the baselines is just typical non-neural baseline we use for all the shared tasks, which just does simple alignment between the lemma and the inflected form. And then for each slot, it basically takes the most popular transformation. And also some strong neural baselines, such as neural transducer, which is essentially a monotonic attention model, and a transformer adopted for character level tasks. So with some variations, when we augmented the data with hallucinated data from the approach that I described earlier, and also that were trained with family-wise shared parameters. So it means the model was trained on several languages at once. So, and we received 22 systems from 10 teams. Most of them were now neural, so unlike in 2016. And most of them use some form of hallucination data for low resource languages, especially, and multilinguality, like in terms of the training of the systems. So, and some of the models that were submitted, they just improved our existing neural baselines, for instance, the decoding technique, and some like fine tuning over family. And ETH Zurich was also improved the decoding strategy. And some systems presented some improvement over Hartman atonic attention model that I described earlier. For instance, Flexica used a multilingual model with improved alignment strategy and some data hallucination based on phonotactic modeling. Some other teams, they improved their own models from previous years. So one of the strongest submissions was from DeepSpin that trained a massively multilingual model with some form of sparse marks instead of soft marks. And some other teams, they also compared transformers to just LSTM encoders, decoders. And some other models, so also very strong submissions, they use ensembles of transformers. For instance, CU-Link, one of the winning systems, use ensemble of 3 monolingual transformers augmented with the input where the lemma was replaced with some other non-lemma spots, so that this model can learn some principal parts of paradigm, because sometimes lemma is not the most informative form. And of course, there are some non-neural systems. And one of the interesting submissions came from CU Boulder. They manually developed final state grammars for 25 languages. And there was also a submission from Flexica that improved one of the earlier models based on the transformation rules. So in terms of evaluation, we just looked at accuracy and Levenstein distance. And we see that the best performing system, the UIUC, it reached almost 90% accuracy. And if we look at Oracle, so Oracle means that we basically take into account all predictions. So we estimate our upper bound. So we see still there is a gap between the best performing system and Oracle's. So there is some space for improvement, especially for Algic, Ottoman-Gian, Sino-Tibetan, Southern Delhi, Uto-Aztecan families. So if you look at the accuracies per families, so we see that some families such as Niger Congo, they performed really like almost 100%. Whereas some other families, such as Uralic or some Native American languages, they reached very low accuracy. So, and some of the teams, they looked at specific research questions. So again, the CU Boulder, they compared the manually designed final state grammars. And the conclusion was that the paradigms of some languages were relatively easy to describe, but neural networks also performed quite well on them. Whereas those that were challenging for them and for, so such as Ingrian and Tagalog, so they were also required a lot of amount of person hours. So, and of course, many teams, they try to improve their low resource language performance. And they found that hallucinated data helped, and augmenting the data with tuples where lemmas are replaced with non-lemma forms also helps, and multilingual training, and of course, ensembling. So, and in the unimorph, the data is also not 100% clean. So we had some systematic errors due to that. And also some dialectal variations were present in Finno-Ugric and Tungusic languages. Talking about specific languages, so what kind of challenges they were. So for instance, for Cree, the paradigms were very large, but with very few lemmas. So it was really hard to learn them. For Niger-Congo, this almost 100% performance probably can be explained that the data came from some textbooks that most likely provided some almost most regular forms. So we need to also just take it very kind of carefully, this conclusion. So in terms of Tibetan language, so majority errors are related to allomorphy, also some impossible combinations of component units, because the Tibetan has like two-dimensional kind of script shape. So it was a bit challenging. And for Evenki, so it's one of the languages with least standardization of the oral speech transcription. So it was a lot of variation in this way, and in terms of the consistency of annotation. So to conclude, submissions were able to make productive use of multilingual training. Data augmentation techniques such as hallucination helped, and combined with architecture tweaks like sparse marks, it also helps. And in some languages such as Ingrian, Tajik, Tagalog, Zarma, Lingala, so hand-encoded linguist knowledge in finite state grammars resulted in best performance. So, and I also wanted to suggest some further readings from linguists who analyze these systems. So one is about from Elsner and Andreas Sims. So what this sequence-to-sequence framework can contribute. And the second one is from Rob Malouf about such lexical databases like Unimorph. So finally, so in 2021, we are organizing a shared task. So we are trying to improve this annotation for under-resourced languages and extract data from finite state transducers such as Apertum and from grammar books. And in the second part, so we'll try to work on human-like generalization and organize annotation for WAC tests across languages together with Ben Ambridge. So if you're interested either in participation or annotation, so feel free to contact us. Thank you.
Thank you. So, Ekaterina, what is the plan? Would you like to take questions now, or will Ryan give the second part of the presentation and we hold all the questions afterwards?
Maybe let's ask Ryan if he wants to just present now.
I can present now if you want.
Okay.
So can you make me co-host, I guess? So I can share my screen. Can you guys hear me all right?
Yeah.
Yes, perfect.
Can you share your screen?
Yes, I need to be made co-host, I think. Oh no, I don't, do I?
Sure.
No, let me.
For me, it worked. Okay, I'm not.
It depends on the Zoom settings. Let me see. Can you guys see it?
Okay, yeah, it works.
Okay, so see if this is all going to work. So this is part 2. This is my, or who am I? I'll talk a bit about myself. So my name is Ryan. I deeply just prefer academic titles as a general rule. So people often email me and I can, but please just call me Ryan. So I do work at ETH in Zurich. Before that, I spent a year at Cambridge, and then I Brexited to ETH, and I did most of my degrees, or all of my degrees, at Johns Hopkins in Baltimore, Maryland, which is my hometown. What I probably should have added to this slide is that I lived in Russia for about a year, many years ago, and I guess my first degree was originally in Russian literature before it changed to cognitive science, and then it moved to computer science along the way, but that was at Johns Hopkins. So it's sad I couldn't go back. Or I guess I will eventually, but the virus has prevented our traveling. So yeah, when I was in Russia, I studied at St. Petersburg State University for a year. So not really Moscow, but I was in Moscow a few times. It's fun. But anyway, in case you don't know Baltimore, I had a picture. It's allegedly the greatest city in America, which is kind of a bit of a propaganda piece if you've ever been there. But they decided to paint it on our benches, which I always found funny because it has one of the highest murder rates in America. As opposed to fixing the problem, they, in a good American way, they just decided it didn't exist. And they spray painted some propaganda on our benches. But other than that, it does have some beautiful places, my hometown. Anyway, so thanks to my amazing collaborators who, with whom the work in this talk is going to be, or with whom I did the work in this talk. Okay. So yeah, I want to get right into it. So typically when I give talks, I've thought very hard about how to give talks recently, and I realized I just don't think I have the ability to give an overview because it's just not in my nature. I really have to go into a subject in depth just for me to understand it. So what I'm going to talk about today is the arbitrariness of the sign. So this is actually based on a single paper, which I'm going to talk about for my portion. It's the paper was runner-up for best paper at ACL last year. It did not win. And it also had a lot of criticism, so it's not that universally viewed as a great work, but nevertheless, it at least some people liked it. But I'll send around the link if you guys want to look at the paper more directly. But what we researched was the arbitrariness of the sign. In my introduction, I thought it was interesting because it's always weird to hear yourself introduced, but what I really like to do with my time is I like to think very hard about linguistic theories and come up with more mathematical formulations of them, which is what how I was presented, which is quite accurate. So this is sort of an example of that. So to go back to the arbitrariness of the sign, which perhaps you guys have all heard of, it is a sort of an idea that goes back to the linguist Salsur, 1916. That's an interesting date because that's actually the date I think his book was published, but it wasn't actually his book. So he never wrote anything in his lifetime. He was just sort of a lecturer who taught a lot of students. And then after he passed away, his students sort of put together a book and published it under his name posthumously. So Salsur hypothesized that the form of a word, the signifier, has little relationship to its meaning, which he called the signified. You often hear the signifier here in English, the French word. And this is sort of regarded as an instance of duality of patterning in language. So sort of that words, they have sort of, they have a symbolic meaning, but the individual units can be composed to give words. And arbitrariness is generally viewed in the cognitive science literature. So these citations down here, do I have my pointer? Yeah, these citations down here as sort of a really good idea, sort of a great invention in the scope of language processing, because it allows you to communicate things that are not directly grounded in percepts. So otherwise, if we didn't have arbitrariness of the sign, we would be stuck to things like onomatopoeia, like the fact that a cow's moo sounds like the word moo. Okay, so Salsur was Swiss. He's often mistaken for French, but he was Swiss, and he taught at the University of Geneva. And he's widely considered the founder of structuralist linguistics. So to give a bit of a linguistics history, at least a Western one, which is that Chomskyism sort of supplanted structuralism in the 60s, but structuralism was very much, it still stays with us. So the structuralists, they brought us tautologically structure. They brought us the phoneme. They brought us the morpheme. They brought us these units of structure, and that's what they were all about. And Chomskyism was sort of built on that structure. So let's get into the theory before I talk about exactly what we're testing and what we came up with. So the general idea, to put it more concretely, about the arbitrariness of the sign is to say that a word's sound waves, or sort of the signifier, is different than what it refers to, like, cat. So this is not actually the sound wave for cat. I think it's actually a sound wave for a cat purring. So it doesn't look like human language. but in case you guys can read IPA, and we're going to note the meaning as V for vector, and that's going to be something like Rn, so maybe like a word vector. So the arbitrariness hypothesis is sort of saying that these two things, these two columns, don't have a generic relation between or a consistent relation to them. Okay. So the entire paper, in a nutshell, sort of like one slide, is that, well, we sort of know that isn't quite true. We know of a lot of sort of non-arbitrariness. To give an example, in a lot of the non-arbitrariness is morphologically driven. So, you know, like verbs tend to end in the same endings, infinitives tend to end in the same endings, and these sorts of things. But maybe there's some other sort of non-arbitrariness. And we sort of said, Salsur sort of put forward that, you know, the sign was completely arbitrary, but we're asking a more nuanced question. We're asking, how arbitrary is it, and how can we measure that? That is there, to what extent is there a predictable relationship between a form of a word in a language and its meaning? And we suspect it's not a lot. So the reason you should suspect it's not a lot is because when you're learning a new language, you know, you still have to memorize the words. But nevertheless, you know, if you think about the long tail of language, you think about, say, something like the Jabberwocky by Lewis Carroll, we're still very good at guessing, you know, some of what these words mean, right? At least when you read that as a native English speaker, you say, oh, what a borough, well, that kind of sounds like a tree or a thing. And, you know, like we have a general sense of what these nonce words can mean. So maybe there's something there. So maybe there's some sort of pattern, and maybe it's 10% or so of the sign is guessable. The meaning is guessable from the sign. In other words, to be more scientific, we're trying to rigorously operationalize and test this thesis. So the hypothesis that the sign is arbitrary. Just to get into a bit more about the linguistics, there are different types of non-arbitrariness and associations, and there's a lot of great work that sort of catalogs this and taxonomizes it. So morphology is sort of the most trivial kind of non-arbitrariness of systematicity. Like in Portuguese, all verbs end in AR, ER, and IR. You know, phonostemes, this is a bit more interesting. So in English, there's this posited group of things like gleam, glow, glisten, glass. They all have to do with light, and they begin with GL. So maybe this is sort of a non-morphological meaning-bearing unit. Now, if you think about this, like morphemes, one definition of a morpheme that gets touted around is that morphemes are the smallest meaning-bearing unit. So this sort of flies in the face of that because it's clearly not a morpheme. It's a bit smaller, and it appears to bear some meaning. And also iconicity, something like onomatopoeia. So meow sounds like the sound a cat makes. So there's also some cross. So these are within a language. Although this one, iconicity, probably should go over there. But general arbitrariness is general patterns in word forms across the word. So like there's a non-trivial, to go to the third bullet point, there's a non-trivial relation or percentage of the world's languages where the word for tongue starts with the word L. Or in every language that I know, except for maybe, I think, Georgian in the Caucasus, that the word mama means mother, where in Georgia, it means father, I think, in Georgian. You know, the hypothesized sources of these associations are sort of the shared neurocognitive architecture or similar experiences. But, you know, at some level, this is sort of speculation. But this paper focuses within one language, so systematic patterns within the language. So the best example of systematicity of this type is a phonosteme, because you would not expect, for instance, that GL has the same meaning in this sort of same clustering in Russian. It's not like a fundamental fact of those two sounds. It's an English specific thing. Okay. So I mentioned this before, but what we really want to avoid in this talk is trivial systematicity. So So I don't have to tell you, as I said before, I don't have to tell you that morphology is systematic. That's how we're able to learn it, right? When I learned Russian as a second language speaker, they gave me big declension and verb tables, and it was systematic. The test was generalizing that knowledge to new verbs. Of course, this is true. And we don't want to pick up on that, because a finding that says morphology exists is, well, it's not very interesting now, is it? So we want to figure out also a way in the method I'm going to propose. We're sort of building up to this method where we control for inflectional morphology. We also want to control for derivational morphology. So English words that end in ation, well, they tend to be abstract nouns. So we don't really want to pick up on that either. So we really want to identify things like phonostemes. And again, the goal is to come up with a general method that allow us to measure this and hopefully find some novel conclusion. Okay. So to go back into phonostemes a bit, because I think this is really the best example of sort of systematicity in a language. So phonostemes more formally are subword level units that correlate with meaning. They're not morphological. So over, as in like overlook, overthink, overeat, this is not a phonosteme, although the relationship here is actually probably more complicated than you might think, because when derivational prefixes become non-productive, they might become fossilized and end up as a phonosteme. So glisten, gleam, glitter, gleam, glow, glint. This is the one I mentioned before. F is another one. Flap, flare, flee, flick, fligger, fling, flip. So these have very much a movement vibe to them in English. And these are productive. Again, I mentioned the Jabberwocky before, but if you make up a poem in English with made up words, you can evoke these meanings in the minds of the listener. So there's something there. There's not a lot there, but there's something. And I think that's why much of the literature has, that's why the literature has spent time talking about these things, right? Okay. So the unanswered scientific question, at least we thought it was unanswered. We looked at the work in the literature. We didn't find it was very satisfying. Is there a non-trivial, that is something we can measure, presence of phonostemes in languages' lexicons? So to operationalize this information theoretically, because we'd like to come up with a very clean definition that we can measure. So I talked about the notation earlier, but we're going to introduce some more. So let capital W be a signified random variable. Remember before I said little w was an individual value, and let v be a signified valued random variable. And I said little v was a value. So we're basically saying that what Salsur claimed was that the mutual information between W and V is essentially 0. So this sort of is saying that this is something about a mutual information, a quantity from information theory, means we can suddenly test it. So now once we sort of said, okay, this is what we're really asking about this mutual information, we now get down to engineering questions like how do we define W in a way we can compute it, how to define V, and of course, how do we approximate this? Because this is in general going to be very hard to compute, right? If you have a word that can range in sigma star, you're going to have an infinite sum. You're going to have an integral. You're going to have some nasty stuff. So this is probably before. So I guess sort of the one side which people know why I think better is the more elaborated in the paper. So a lot of people are side. Operationalization, and we sort of think this is the way you ought to think about it. It's just sort of a very clean way of considering the problem. So previous work has some arbitrary decision points, like how do you measure phonological similarity? So what you see in these other papers is you see something that has something like edit distance playing a role. And edit distance is problematic if you think about it, because it's not a language independent metric. You say something like Arabic and root template patterns, these things, it's very ad hoc. So in general, mutual information doesn't care about things like that. If you can approximate it well, it'll just ask about pure predictability. Measuring semantic similarity is sort of ad hoc as well. Like people will try and correlate edit distance and cosine distance and things, but then you have all these hand-defined decisions that people made, and we wanted to sort of avoid that by having a much simpler, clean definition. And also most of these frameworks, these models, they mostly focus on linear models. So sort of as is you might have expected, because we're doing modern NLP research, we're going to have some neural networks in here, which are going to be able to learn nonlinear relations. Okay. And finally, this bullet point here, we don't really think that those previous works had an adequate mechanism to control for trivial phonosteme, say morphology, which is something we were able to introduce. Okay, so that's sort of like what's wrong with the competitors. Now I'm going to tell you why we really like mutual information. As I said, there's no need to define the custom distance network, distance metrics, the nonlinear relations, and we can control for different factors through conditioning. For instance, if we have we basically use the standard cross entropy approximation of mutual information. That is, we basically evaluate the model, two different models on held out data. So we can approximate H of W with a language model and H of W given V with a conditional language model. So this is really just trying to have a model that's no different than the other language model that's predicting, it's trying to place high probability in a word. So that's the language modeling task, place high, a character level language modeling task, but trying to place high probability on held out words and then placing high probability on held out words given meaning. And their difference is sort of an approximation of mutual information that becomes exact as we see a lot of data. So to give you an example in the NLP literature, what a conditional language model would be, things like machine translation or dialogue, chatbots, these are all conditional language models. Machine translation, we condition on the input and try and predict the output sentence. So we provide experiments on the CLEX data set. So this is by Harold Bayan, which is a popular word level corpus. There's data for free related languages. Of course, that's problematic. We don't really get a wide picture of the different things that can occur. But at the same time, there is quite a bit of research on phonostemes that pop up in these three languages. So we can sort of qualitatively validate what we found. Importantly, this is annotated for morphology and it's transcribed in IPA. And we're going to use language-specific word-to-vec vectors. That is, we trained on data in that specific language as approximation of meaning. So on CLEX, here's what we found. Controlling for part of speech tags. So this is what's here. We looked at a normalized mutual information. So this can be interpreted as a percentage. And you can see that we get between 2 and 5%. This number is a bit interesting. Why is this so much higher? A lot of this is in our expectation was fossilized derivational morphology. So an example would be, I think I have a slide on this later, but an example in German would be the prefix but, which isn't productive, but nevertheless corresponds by making a verb transitive. But this is sort of the thing we were expecting to see, right? We didn't know exactly how big it would be, but we expected to see something that was significant. So these values are significantly different than 0, but we expect it to be small. So that sort of corresponds to our intuition. And we sort of argued that this has an answer to Salsur's hypothesis in the sense that the refined version of his hypothesis, which is basically how arbitrary is the sign. And now we talk about how to measure that. So we also experimented with North Eurolex. So if you haven't heard of this data set, it's quite amazing. It's basically like a Swadesh list in about 1,000 languages. That's what 1,000 or so, or maybe it was 100, sorry, 1,000 words, but it's still big, got them backwards. But it's in mostly European and Asian languages, and you can download it online. So we tried to run this on a wide variety of languages, and we found similar things. We have some problematic bits to this experiment. We had to use English word-to-vec vectors as an approximation for lexical semantics in this word. They are concept aligned, so we can use the English vector for fire for, say, Russian word for fire, like go on. But of course, this is problematic because that's not an actual representation, but we hope this is okay given that we have these are basic concepts, and there's this issue that for many of these languages, like say Manchu, there isn't a lot of data to train word vectors in Manchu. So this was sort of a clean experiment, as is the same across all languages. And we find sort of this. This is the interesting one. This is the difference between these two curves, or say this is the normalized bit one. So these are the same. This is normalized. The green curve is with part of speech tags not being controlled for, so there's no conditioning up there. This red one, where we control for part of speech tags, you can see that a lot of the languages have as the cross-linguistic computational research, right? So, I mean, Kat sort of got into this with the morphology annotation, but when you start saying, okay, we want to do research in a very quantitative, data-driven way on hundreds of languages, you know, every language, every data set, I should say, has its own story. It has stories of the annotators who made mistakes, this, that, you know, there's always an issue, and the data is clean, and making data is an ongoing process. So linguists like to criticize us. Actually, I have a slide about that, do I? We'll save that story for later. But anyway, linguists, you know, they always say they like to pick out individual problems with individual data sets, like say, you know, the data in your Tamil bit isn't quite accurate, but we sort of say, yeah, that's true, but I don't think we'd expect to see a consistent effect in this many languages just because of noise. You might get that in one language, but by running this on very many languages and we see a consistent pattern, the standard we have for evidence is quite high, because you can't just throw down arbitrary hypotheses and see them come out true in this such a percentage of your languages. Okay. So now I'm just going to do the qualitative bit to sort of see, like, a question we asked is like, okay, what did this thing find? So we have this model, you know, I said mutual information, I said this nice equation, and I said there's some neural networks that approximate it, but what did it find? So we had a methodology that we developed to sort of try and figure out which phonostemes were prefixes and suffixes. The suffixes we got by flipping the word were statistically significant. So I'm just going to write to the plots, or sorry, the diagrams. And what do we see here? This is English, and well, we see things like, you know, the two most famous ones in English pop up. So this was sort of really great to see, when you sort of see that the things you thought there. You can see he was saying how it doesn't actually get that effect. So I thought that was interesting. But we see this is the suffix. This is, a lot of these are sort of known phonostemes. And here's an example of what I mean by fossilized